don't know if it is.
No.
Maybe, yeah. I think. Great, okay.
That's
Cool.
Shall we?
Sure, yeah.
Okay, well, thank you all for coming. This week we have a little bit of a special presentation, right? So Jordan Snyder is a graduating, so I guess Professor Snyder at this point. Dr. Snyder.
Doctor, come on. Don't have the job title yet.
Working on it though, right?
Yeah.
So he got a postdoc position at the University of Washington. And so he's going to talk to us today about collective dynamics on networks in general.
Yeah. Okay, hi everyone, thanks for being here. I'm really glad to be talking in the Student Run Math Applied Math seminar because it's been my favorite seminar. Overall, I just like how we get to talk to each other about our research and have pizza every week. I'm going to tell you basically the whole story of my PhD from start to finish. The structure of this talk basically mirrors the structure of my dissertation. There's an intro, there's 3 chapters of stuff, and then conclusion. Just right off the bat, I want to thank the funding sources that let me do all this, the Army Research Office, and then the Center for Nonlinear Studies at Los Alamos over the summer, because they made it possible. And I'm here at UC Davis. But you knew that. So let me rewind to the start and talk about, let me put my cursor where it needs to be. Okay, so what's the point? It's a great question. This is a slide from a presentation I attended when I was an undergrad as a senior at Rensselaer by Peter Persons. Does graduate school make sense for you? Why do you want to go to graduate school? So it's listing out some good reasons and some bad reasons. The bad reasons, you're good at academics, you want to keep doing that, just hitting that dopamine lever of being good at tests. You're scared of going out into the world, and it's a way to put it off. Good reasons, you have a career in mind, and you need a PhD to do that career. Another good reason, you want to understand the world at a deeper level. When I saw this felt like cheating. Like, I don't understand anybody who would say no to this, right? Like, of course I want to understand the world at a deeper level. So I'm here. But there's a lot of nuance under this. What is really understanding? I think that's a very difficult question to answer. Anybody want to offer some perspectives before I give mine? Adam, anything? Yeah? Okay.
Knowledge claim that expresses concordance with reality.
Knowledge claim that expresses concordance with reality. That sounds good, yeah. Knowledge is important. Here, Isa.
Accumulation of data.
What's that?
Accumulation of data.
Accumulation of data. Okay, that's a more like consciousness agnostic point of view. Yeah, totally. So in my view, understanding means you can tell a story that makes sense. You can explain why something is happening in plain English. But this notion is inherently subjective. This means making sense is a subjective notion. And as Dimitri alluded to, this is related to prediction and control, but I don't think they're synonymous. You can predict and control something without understanding it, and vice versa. So one question is, how big of a leap is allowed? So for example, if we completely nailed the grand unified theory of everything, we knew all the subatomic particles and how they interact, could we have claimed to understand the whole world? I claim no, because we need to explain emergent phenomena. We need to understand how the fundamental pieces come together and why they form large-scale structures that they do, like people and math departments and fire extinguishers and whatever. So a little bit about emergence. I'm going to refer to this classic essay from 1972 called More is Different. This is by P.W. Anderson. So he's pointing out this very intuitive thing that I think we all sort of have in mind at some level, that sciences can be arranged in a hierarchy where the elementary entities of science X obey the laws of science Y. So he's saying that solid state or many-body physics is built up from elementary particle physics. And then chemistry is built up from many-body physics, and so on. So at each level, you're not really getting anything new necessarily. Well, You are. So what I mean is, when you go up this hierarchy, you pass to a simpler description that lets you see more directly the things that you might be interested in. So this is what I want to understand. For a more contemporary perspective on this same issue, I'm going to refer to Randall Munroe, author of the XKCD comics. This is one of my favorite of his. So we've got a stack of scientists, from sociologists all the way at the left, psychologists saying, psh, sociology is just applied psychology, and then backing up until you get to a physicist saying it's nice to be on top, and then a mathematician over here being even more high and mighty. Oh, hey, I didn't see you guys all the way over there. So what I want to do in this language is understand the map from X to applied X, where X is a science. Okay. So any questions on why I'm here, I guess? Okay. I want to point out that I have done nothing even close to this in my time here, so there's a lot left to do. Sub-goal, don't be this guy. Liberal arts majors may be annoying sometimes, but there's nothing more obnoxious than a physicist first encountering a new subject. Oh, you're trying to predict the behavior of complicated system? Just model it as simple objects, and then add secondary terms to account for complications I just thought of. Why does your field need a whole journal anyway? So I don't want to do this. I don't want to sweep away real complexity and just say that I understand everything. Okay, so an outline of what I'm going to tell you. I'm going to tell you about 3 chunks of work that I've done that aim to illuminate something about collective behavior. First is called coupled entrainment. So I'm going to tell you about coherent motion and heterogeneous population of oscillators subject to global forcing and coupling. So I'm going to tell you about the interplay between this top-down and bottom-up modes of organization. Then I'm going to tell you about coarse graining. So here, what I'm focusing on is synchronization as a reduction of dimension in the behavior of a dynamical system. And I'm going to tell you about discovering effective laws of motion for those fewer degrees of freedom. And finally, I'm going to tell you about cascading extinction. So this is a sort of discrete dynamic on a network. The point there is that networks of interdependence among individuals can lead to global cascades, and the topology of the network, jointly with the initial conditions, determine the outcome. Okay, so let's jump right in, coupled entrainment. This is a very not profound slide. This is what I mean by an oscillator. Theta dot equals omega. I just have a phase variable that advances linearly in time. And we can solve this with 0 effort. Theta of t is initial phase plus omega t mod 2 pi. Okay, nothing profound. And it looks nice in the complex plane. If you take z equal to e to the I theta, then that z variable evolves according to this I omega z. So if you see a z dot equals I omega z, think rotation. Okay, that's the whole story. Now let's add forcing. Okay, so we've got a phase variable advancing with a natural frequency, but then it's subject to this external forcing v, which is at a frequency capital omega, different from small omega. And v, this function v is 2 pi periodic, so that omega is explicitly the frequency. Then this z thing is called the phase response curve. It tells you, given whatever phase my oscillator is at, how is it affected by an input force. So the solution, it's a little more tricky. You can approximate it by this. So what this says is that under certain conditions, the oscillator will respond by moving at the forcing frequency plus a phase offset. So that's going at big omega t plus a phase offset. That offset then evolves according to another ODE like this, where this delta omega is the frequency detuning. It's the difference in natural frequencies. And this lambda thing is the interaction function. It just averages the influence of the forcing function over a whole cycle. Okay, so what you can see is, say that this curve is what the interaction function looks like as a function of phase. And let's say my frequency detuning has this value. Then this ODE can have a stable fixed point. And if that's the case, then the original oscillator is going to be moving at the forcing frequency plus a constant phase offset. And what I'm going to call that is entrainment. Also, this equation gives you some sort of an estimate of the maximum frequency detuning. So if the natural frequency is too far from the forcing frequency, you won't have an intersection here, and so you won't be able to see entrainment. So this gives you a first order estimate of that effect. All right, so if I have a population of oscillators that I apply the same forcing frequency to, these oscillators can have different frequencies. Let's say that they are evenly spaced from -1 to 1. And if let's say that my interaction function has this sawtooth form, then I can get a situation where the phases, where everybody's entrained, everybody's moving at the same frequency, but the phase offsets are spread uniformly from, say, -pi to pi. So I have identical frequencies, but maximally different phases. I'm calling this state entrained decoherence, and this is a case of top-down organization, because I have a global forcing function that is applied to everybody, just top-down. So another way that a population of oscillators can come to behave coherently is by coupling. And the fundamental model of this is the Kuramoto model, which is this ODE. So again, I have natural frequencies for each oscillator, and then coupling according to the sine function. And this K quantifies the magnitude of the coupling. So the key features of this are heterogeneity. I have different frequencies. Typically, they're sampled from some distribution of natural frequencies, and the coupling is attractive, so it drives phases together. These trade off influence depending on the size of K. The way you measure that trade-off is by the order parameter. So what I'm doing here, to visualize the order parameter, I just stick each phase on the unit circle in the complex plane, and then I take their center of mass. And that gives me a vector like this. So the length of this vector, so the magnitude of this complex number, gives me a measure of organization. I'm going to call this length R. And I'm going to remark that this organization is bottom-up. So it's just all of the pairwise interactions coming together to organize the population. So the classic result here is that depending on the value of K, you get this phase transition in the order parameter. So for small k, you get no particular preferred phase. R is near 0. For very large k, you get everybody basically at the same phase, and R is near 1. And then in between, you get this trade-off, and the order parameter departs from 0 at a critical value of coupling strength. Okay, so I'm going to now combine those two effects. Entrained decoherence with coupling. Okay, so here's my ODE. I have natural frequencies that are evenly spaced from -1 to 1. I have the sawtooth interaction function, and then I have sinusoidal coupling. So due to the symmetry of this phase configuration, this entrained decoherence state is a fixed point for all values of k. Basically, the coupling forces balance out. And I can take the Jacobian and study its stability. So turns out the Jacobian can be diagonalized exactly for any value of n. This took me a little while to realize, including infinity. I'm not going to show you that math, but let's talk about it later if you want. So what I found is that the entrained decoherence state becomes unstable at a critical value of 2 over pi, when k equals 2 over pi. So once the coupling is that strong, the oscillators start to group together. So how does that compare to, say, the unforced case if I don't have this forcing signal? And that's what I'm showing you here. So here's that same sort of phase diagram as I showed on the previous slide. So if I apply forcing, I see R equals 0, so I'm in the entrained decoherent state until 2 over pi, and then I depart, and I get non-zero R. But if I don't have the forcing, it takes me all the way up till 4 over pi to get phase alignment for the same choice of natural frequencies. So even though this forcing function was designed specifically to keep the phases different, it's actually facilitating the alignment of phases before I would see alignment of phases in the unforced case. Okay. So that's pretty much the whole story. Takeaway: there are different routes to collective behavior. I can make coherent motion happen in a top-down way or a bottom-up way. And even though global forcing can spread phases apart, it's actually helpful in creating alignment of phases. It can work synergistically with the coupling. And another interpretation you can take from this is that frequency and phase alignment both matter. And frequency alignment in particular is not directly captured by this R order parameter. So I can have everyone moving at the same frequency but have a very small value of R. Okay. So any questions on this? I'm gonna try to take questions after each section because it's gonna be a little bit disconnected.
So you get when you have forcing and coupling, and then you see that critical transition at what was it, 2/π?
Mm-hmm.
Is that discontinuous? Because I mean, it looks like it jumped straight to
Yeah.
0.6. Okay.
It is discontinuous, and actually, it's pretty funky. So for finite n, there's actually a tiny little hysteresis loop where there's an unstable branch like this, and then it turns stable over here, and then the width of that loop shrinks as you increase n. So in the infinite n limit, it's exactly just a discontinuous jump.
Cool.
And also for this particular choice of natural frequencies, it's also a discontinuous transition in the infinite n limit. Yeah. Cool. Thanks. Anything else?
And this is on the all-to-all coupling?
Correct. Yeah, this is all-to-all coupling. That's right. Okay, cool. So moving on, coarse graining. So what I'm talking about in this section is learning low-dimensional models for a high-dimensional system. And I'm going to, again, the general problem here is, given a high-dimensional time series, is there an effective low-dimensional representation? And if so, what is it? And for me, this is one way to talk about collective behavior. If I have many degrees of freedom, but I can effectively describe them with a smaller number of them, then I can say, this system is behaving collectively, and here is a better description of it. Okay, so this is my attempt to sort of go directly at this, like, moving up the hierarchy of sciences thing. But of course, I'm going to do this in a very limited sense, in a certain specific situation, because the general problem is hard. So we don't necessarily know, in general, that there is an effective theory to be found. Even if we know that there is one to be found, we don't necessarily know its dimension, or the map that gets us from the original degrees of freedom to the new ones, or the form of the equations we should be looking for. Should we try to find an ODE? Should we try to model some part of it as noise? Do we need a PDE, and so on? So as a first step, I'm going to take a very simple case, which is, again, coupled oscillators. So I've already told you about the Kuramoto model, and what the feature of that I want to introduce now is its low-dimensional behavior. So it turns out, due to some work by Ott and Antonsen, that in the infinite n limit, you can describe the entire population with a single ODE. So again, I have the Kuramoto model here, and here's the order parameter z. I'm going to keep the whole complex number and not just its magnitude. So it turns out that in the n to infinity limit, the order parameter obeys an autonomous ODE. In particular, if the natural frequencies are sampled from a Cauchy distribution with center at omega and width delta, then this is the ODE. And by the way, I told you to remember I omega z gives me rotation. Here's an I omega z right here. So the order parameter itself has this rotation at the central frequency. And then the width damps it towards 0, and the coupling destabilizes the 0 point and drives the order parameter towards r equals 1. So you can read the physics off of this equation. It's wonderful. So here's a one-dimensional ODE. This is we can go a little further though. We can actually change the coupling structure and have it be modular. So what that means is the oscillators are divided up into groups. Here I have 3 groups of 5, such that the coupling strength is stronger for oscillators in the same group and weaker for oscillators in different groups. And that's expressed right here. So this is just the same Kuramoto model with just a different coupling structure. Okay, here sigma runs over the groups, and J runs over the oscillators within a group. And again, I'm going to give an order parameter to each module. So here's going to be Z1, Z2, Z3, or sorry, 0, 1, 2, because I'm working in Python. I just have M order parameters, or M is the number of modules. So it turns out the same ansatz can actually give you equations for these variables. And if within you can actually have a different distribution of natural frequencies within each module, and then you get this coupled set of equations, where you have an on-site dynamics and then coupling. Okay? So this is great. Again, you can read off the physics. It's a nice equation. This relies on the population average behaving deterministically. So it relies on the n to infinity limit. So what I want to know is, does this reduction work for small n? And schematically, my question is this. If I literally have 15 oscillators, can I replace them with 3? Okay. So, to answer that, I looked at some numerical experiments on 15 oscillators. And just to be super clear about what I'm doing, I sampled natural frequencies. I used a normal distribution, not a Cauchy, sorry. But I fixed the natural frequencies for all experiments. And these are those natural frequencies. So here's the node index. Here's the nodes in the first module, second module, and third module. And this is their natural frequencies. So they range from like -1.5 up to 2. Not too large of a spread. And I'm going to leave myself 2 control parameters, K in and K out, defining the coupling strength within a module and between modules. So I'm just going to see what happens, right? And what does happen? Well, I'm going to show you. I'm going to hit play in a second, and these dots are going to start moving. So here, the color indicates the module membership, and they're just each a phase on the unit circle. And I'm varying K in and K out. So here I have large K in, small K in, small K out, large K out. So, right, so if coupling strengths are weak, then you don't get very much coherent at all. If you have large coupling strengths, you get global synchronization, and it's boring in a different way. If you have large K in but small K out, you get something like this, where each color you can see basically appears to be moving coherently. So this looks like a region where the answer to my question might be yes. And then over here, if you have large K in, large K out, and small K in, you get that basically the dynamics don't really respect the modular structure of the coupling network. So I'm going to show you these videos again, but I'm going to give you the locations of the module order parameters for these stars. So this blue star is the center of mass of the 5 blue circles around the ring. I'm going to hit play here. Right. So again, these stars are just pins to certain locations. They're doing boring stuff. Here, each star is sort of reflecting the average location of its module, and they're behaving coherently. Over here, they're just swimming around. And then this, in this case, this is kind of cool. You have this one red guy slipping with respect to its neighbors, and that gives this little precess to the order parameter. Now, in the n to infinity limit, the influence of any single oscillator is going to be tiny. So that precess is going to be smaller the larger n is. But it's significant when n equals 15. Okay. So I want to make I've shown you visually what I mean. Let me make it a little more concrete. My question quantitatively is, given a time series of all the phases, my question is, do the order parameters evolve according to an equation of this form? So given the phases, I can compute the cluster order parameters and compute their time evolution. And then I want to see, does an equation like this work? So I can check that using just a simple least squares procedure. I know there's at least one optimizer in the audience, so the choice of a least squares loss is not actually principled in this case, right? It does not reflect a actual modeling assumption of, say, normally distributed noise. But I'm going to do it anyway, because I would like to. So I'm going to compute the time derivative of the cluster order parameters using just finite differencing. And then I'm going to compute, so this right-hand side is made up of certain functions of z. So I'm going to compute the values of those functions and put them as columns in a matrix. And then I'm going to solve for a vector of parameters to try to get this right-hand side to match the left-hand side. And then I'm going to use the residual of that problem as a measure of how well the dynamics actually are governed by an equation of the form I want. So I'm going to call this training error, and small training error means that the dynamics of the course variables are nearly autonomous, and moreover, nearly autonomous in the form that I want. Okay? So sometimes you get junk, unsurprisingly, based on those couple videos that I showed you. So what you're looking at here in red are, in the solid lines are the time derivative of each cluster order parameter. I've taken the real part. And the x's are the closest I can get by fitting a function of the state in the form that I want. So you can see it doesn't match up very well here. Just for numbers' sake, the log of the error is order -3. Sometimes you get bang-on agreement, and error is order e to the -14. Okay. So I want to understand sort of what makes the difference between these cases. When do I get a good matchup, and when don't I? So if you think back to those videos, a good situation was one where the clusters were each tightly ordered. So to test that, I can look at, given the value of k in and k out, what's the value of the order parameter, what's the magnitude of the order parameter in each cluster? So that's shown in these heat maps for the first, second, and third modules, and then also for the full system. And I'm also plotting the training error. So in the lower right, this is where I get global synchronization. Training error is order e to the -30 or 40, so it's very low, and also all the order parameters are near 1. And then we get sort of a transition to higher error, smaller order parameters. But if you notice, these transitions look very discrete. So that suggests that there might be a discrete condition that differentiates the cases of when I get different values of training error. So to introduce that discrete condition, I'm going to show you this video. Turns out that condition is phase locking. And what I mean is that within each cluster, there's an arc that contains all of the phases for all time. And that arc has angle less than pi. Right? So, and you can see that. There's this red arc of angle less than pi that always contains all the red dots, and so on. So turns out that phase locking does do a pretty good job at predicting these sort of boundaries in the space of training error. So on the left, this is the same histogram I showed, or same heat map I showed you before. This is showing you certain cases of which modules are phase locked within themselves and with each other. Here, there's no phase locking. I get poor error. And here I get the whole system is phase locked, and I get very tiny error. And you can see this boundary maps onto this one. This boundary maps mostly onto this one. This doesn't show up in the other heat map, so sorry, but this is how it is. All right. So what this suggests is, okay, and then I can break it up in this way. So yeah, I can look at a histogram of the values of training error and code it by the data of which modules are phase locked, and I get this breakdown. So what this is suggesting is that I can use the phase locking condition as a way to perhaps find a different way to coarse grain my variables. Okay? Are we even looking at the right clusters? So I've assumed up till now that those structural modules in the network are the right boundaries along which to coarse grain my variables. That might not be the case. Right. I've just observed that coarse graining performs well when oscillators within a module are phase locked. So maybe we can use that insight to identify clusters. To that end, I'm going to define the dynamical partition to be the coarsest partition of nodes, such that nodes in each partition element are locked. What I mean visually is this. So here's a situation where there are basically two clusters of oscillators. But the division is not following exactly the divisions of the network. I'm still color coding them by which structural module they're in. So I have 4 red nodes in this cluster. The other red node is in the other cluster along with the other 10. Okay. So the dynamical partition need not be the same as the structural one. So I can turn the same crank given that dynamical partition. I can find training error given coarse graining by the dynamical partition, and what I'm showing you is a histogram of the errors that I get. In orange are the errors based on the dynamical partition, and in blue the structural one. So this giant peak of really bad error just goes away. But I still do get cases where the dynamical partition performs poorly. So what gives? Turns out the dynamical partition need not respect the structural symmetries present in the coupling network. So you can have different cases. You can have that the dynamical partition refines the structural one, or the opposite, the structural partition refines the dynamical one. You can have them be equal, or you can have them be incomparable. So so I can also break out the training error I get for the dynamical partition based on these cases. And this is my ugliest histogram. This brown section are the cases where the structural partition is incomparable with the dynamical one. And that comprises the worst cases of error. So what that suggests is that maybe we can do a meet of partitions so that I'm always coarse graining according to a partition that refines the structural one and refines the dynamical one. And if I do that, I get much better error. So the green bars, the orange and blue bars are the same as on the previous slide, and in green, this is what I get if I allow the partition to respect both the dynamics and the network structure. Okay, so I know that was a little bit whirlwindy about trading partitions, but any questions about this? So let me just put the, yeah, Martin?
Yeah, so with the structural one, you're always restricted to 3 clusters, right?
Yeah, right.
The dynamical one, you can have more clusters.
Yep.
So that could also
Yes,
contribute to
yeah. So I should be careful about, which, am I comparing apples to apples? Yeah, that's right. Okay, so to conclude, the equations arising from the odd ansatz and ansatz can also apply to finite networks, apparently. And the precision of that procedure depends jointly on the dynamics and the network structure. So it helps if I know which oscillators are phase locked to which others, and if I know the symmetries of the coupling network. Okay, so moving on to my last chapter, cascading extinctions. So this is a bit of a different direction, also about collective behavior on networks. So where this started was trying to understand cascading extinctions in an ecosystem, and in particular a mutualistic ecosystem. Mutualism is a structural trope that exists across different contexts of systems, and basically it just means entities have mutually beneficial relationships. So classic examples are plants and pollinators. You can also think about banks and debtors, designers and manufacturers, political entities, and so on. Anytime you have entities that engage in a mutually beneficial relationship. So there's been a lot of network-based studies of these kind of systems, and people have noticed that if you treat such a system as a network, each entity is a node, and a mutually beneficial relationship is an edge, the network metrics can reveal some common properties. So in particular, two that have been noticed and studied quite a bit are modularity and nestedness. Modularity means that you can divide the nodes into subsets so that most of the links occur within a subset, and nestedness means that if I have a small number of partners and somebody else has a large number of partners, then the partners that I have are very likely a subset of the partners that other person has. So the set of my neighbors is nested within the set of neighbors of a more popular person. And to first order or to the lowest order, this nestedness can be captured by a broad degree distribution. So the property of there being a wide range of possible values of degree. So you can ask about what's the origin of these network structures, and for that I'm going to defer to Wei-Ran, who's done some really cool work on this. But what I'm going to focus on is what is the impact of those network structures on the function of systems that have that structure. And what I'm showing you here is just a list of different systems. There are a bunch of ecological systems as well as some from the New York garment industry from 1985 to 2003. And this is just listing some gross network properties. The modularity, we do see some that are not modular, so it's not a complete story. And this is one nestedness metric. I should remark that there are multiple nestedness metrics, and they're not necessarily completely comparable with each other. So that's a, yeah. Right. And some example networks come from the Web of Life database. This is a fantastic database. It has well over 100 actual plant pollinator networks. These are the result of years of difficult field work, and you can just download this stuff. It's really remarkable. So each of these networks has between 20 and 1,500 species, and many of them are modular and nested. So to visualize modularity, here are the rows are plant species, the columns are animal species, and a dot represents that they have a mutualistic relationship. You can visualize modularity by saying that the links can be packed into blocks, and you can visualize nestedness by saying that links can be packed up into the upper left corner of the adjacency matrix. Okay, so I said I wanted to study cascading extinction events. For that, I'm going to need some dynamics. So I'm going to use these dynamics. These are taken from some previous work that's been done on mutualistic networks. So Pi is the abundance of plant species I, AK is the abundance of animal species K, and they each have a per capita growth rate that depends on some intrinsic property of that species, competition with the members of its own guild, so plants compete with plants, and mutualistic benefit with members of the opposite guild, so plants benefit from animals. And there's also noise applied to each species. Okay, so we got intrinsic growth and death, competition, mutualism, and noise. The key control parameter I'm going to focus on is mutualistic strength. So there's this matrix gamma that defines the mutualistic relationships, and I'm just going to scale it up and down. So what happens is you tweak that knob. Basically this. So each line here is the abundance of a species as a function of the control parameter gamma 0, the mutualistic strength, and I'm starting it at a high value and decreasing it. So it starts, when it's a high value, everyone can survive, we're all happy. As you stress the system by decreasing mutualistic strength, you start to see extinction events. And these things actually do occur as saddle node bifurcations. So if you know from your 207A or wherever you learned that sort of thing, saddle node bifurcations are preceded by critical slowing down. That means that the system gets less resilient to perturbations. So a perturbation near a fixed point will decay algebraically rather than exponentially. Near a tipping point, the system becomes less resilient. So noise has a larger effect. Basically, noise is a bunch of perturbations, and they each stick around for longer. So the effect is you see higher variance and higher autocorrelation in the time series of abundances. Now, variance is nice, it's a good signal, but if you think about it, we have a bunch of stochastic time series. The variance is just the diagonal of a whole covariance matrix. So in some sense, we're leaving a bunch of information on the table that we could be exploiting, and hopefully, if we know that our coupling network has this modular and nested structure, maybe we could leverage that to get some more information out of the covariance matrix. Okay. And as a little bit of sort of technical backup to that idea, you can linearize these dynamics near a fixed point, and what you get is a multivariate Ornstein-Uhlenbeck process where you have x is the distance from your fixed point, and it evolves according to the deterministic part is the Jacobian, and then I have some noise matrix and noise. And this, you can actually write down the steady state covariance matrix, or at least an equation for it. It's this is the Lyapunov equation. So the Jacobian is related to sigma and is related to the covariance matrix and the noise matrix. And the network properties are going to show up in the Jacobian. So there should be some relationship here. And actually, you can write an explicit formula for the covariance matrix. So that's great. So let's actually go and look at the data and see what happens. So here what I'm plotting is, given a bunch of pairs of nodes, the degree of one times the degree of the other against the covariance between them. And here, this is near a tipping point versus far from a tipping point. And we see a little bit of a difference here. So this, basically, that may actually just be, I see a dot high up, far from the blob. That may just be due to overall higher variance. You can also look at path length. What's the length of the shortest path between any two nodes? And then look at that against what's the covariance between them. And you get some, and I'm looking near the tipping point versus far. And I get some sort of decay in my box and whisker plots, which is kind of cool. I can also break each one of these box and whiskers. Underneath it is a whole histogram of stuff. So I can actually plot, this is network distance 0, network distance 1, network distance 2, and 3. And I can plot the whole histogram. And there's two colors of histogram, near versus far from the tipping point. And then you can also look at among direct neighbors versus, I forget which, what the different cases of this are. Basically, I found a whole lot of not much. It was a lot of pages that looked like this. So found some oblong blobs on log-log plots. So what gives? What happened? Well, we wanted to know about how disturbances propagate through a mutualistic network. Right? That was our goal. The linearization approach is limited. It gives you local information. It says if the system state is right here, and I make a small perturbation, then how will that small perturbation grow or decay? So it can't really capture an entire extinction process where the whole system state is moving a large distance. And it's not clear, well, we have some sort of hints about how network properties might enter in. If I can take modularity and nestedness and frame them in a spectral way, then I could have some hope of pushing that information into the covariance matrix. But we didn't really get very far in that way. Yeah, and my interpretation is that this model was in the uncanny valley between truly applicable and a nice toy model. So it was too abstracted to take seriously in an ecological sense. And then there were too many parameters to get clean analytical results. So there were all these alphas, betas, and gammas, and alphas were sampled according to this distribution, and I chose it because somebody else chose that, and what if I chose something different? What if it was correlated with lots of details, right? So I couldn't get very much. So we decided to change course a little bit and go way simpler. Try to go for a minimal model of population dynamics. I'm just going to model each species as present or absent, 0 or 1. And I do mean present is 0 and absence is 1. That's just to make my notation consistent with other literature that I'm building off of. And my dynamic is that a species remains present only if at least some fraction of its partners are present. So these are mutualistic networks, so I need my partners to be there in order to stay alive. So formalizing that gets you a Watts threshold model, or a fractional threshold model. So UI is the state of species I at time t, at time t plus 1, I'm going to be absent if too many of my neighbors are absent, or I'm already absent, so I can't come back. Extinction is permanent in this model. That's not a necessary assumption. I could say I'm looking at a small patch where I could have species invading back in, but I'm not assuming that. So here, ki is the degree, and theta is the threshold. And so, and then otherwise I just stay present, right? Okay, so something neat that you can do is you can basically approximate the large-scale statistics of this process in a low-dimensional way. So if you assume that your network is described by some set of modules, each one of which has a degree distribution, and there's a mixing matrix that tells you how many links connect each pair of modules. If you further assume that your network is locally tree-like, this is valid if your average degree is constant and your network is large. So the average degree is order 1 compared to number of nodes. And your dynamics are irreversible, that's can't come back from extinction. And your activation probability is monotone with respect to your number of active neighbors. So that's also satisfied by our assumption. Then what we can get is equations for the density of active nodes in each module. And that's shown, and an example of what you can get is shown here. So this is the number of active or extinct nodes in the network versus time. And there's a line, and then there's symbols that are analytical versus numerical. So there's very, very good matchup here. This is work by James Gleason in 2008. So what does the theory look like? I said that we're assuming the network is locally tree-like. So that means I can arrange it into levels of the tree. And for each level, I'm going to give a variable q sub n. And that's the probability that this node is active, conditional on its parent in the tree being inactive. So the way I'm going to update it is I'm going to say, well, there's some probability that I was active to start with. If I wasn't active to start with, then I have some number of chances to be activated from my set of neighbors. And that depends on the q variable at the lower level. So you get this recursion relation that you can iterate to a fixed point and get the eventual state of the system. And then, so the q is a conditional variable, and then I can uncondition it to get rho, the actual density. And here I've assumed that the initial activation probability depends only on the module and not also on the degree. So you can extend this to allow the activation probability to depend on degree. So I've just taken row 0 and just added an index k. And you get formulas that are very similar, just very subtly different. And an interesting thing is that you can actually, so you might think in this setup that you would have to keep track of a variable q for every module and for every value of degree. So given I'm in module I and have degree k, what's the probability that I'm active given my parent is inactive? You don't actually have to keep track of that. What you have to keep track of is a single variable for each module that tells me if I follow a link, if I randomly follow one of my links, what's the probability that the node I end up at is active? And that is equal for all nodes in a module. So this is the computational complexity increases barely at all. So a sanity check, okay, we still get bang-on agreement between theory and numerics. So what I'm showing you here is an example on a network that looks qualitatively like this. I have 4 modules connected up by a ring. So there are no links between 1 and 4 or 2 and 3. These 2 modules have a Poisson degree distribution. The mean is 5.8 and 8. And these 2 modules have a regular degree distribution. So every node has degree 8 in those 2 modules. And the initial condition I'm setting is that 1% of the nodes in the first module are active to start with. And I'm taking a threshold of 0.21. So 21% of your neighbors need to be active in order for you to activate. So if I activate uniformly at random, if I just uniformly at random select 1% of the nodes, what I get is this. So I don't get any global cascade. Here, this is so each curve is the fraction of active nodes in a given module. But if I target the highest degree nodes, if I say I want the 1% highest degree subset of this module and I activate those, then I do get a global cascade. Okay, so I can capture both of those situations with the same formalism, get good agreement between with numerical results. And there's a difference. There can be a difference when you target by degree. So I went and applied this formulation to a specific situation where I have two modules, and I can tune the number of links between the modules, and I can also tune the heterogeneity, the degree heterogeneity within each module. So what you're looking at here, each one of these heat maps, I have mu controls the modularity here. There are no links between the modules, and here there's just as many between modules as within. And here is rho 0, which is the fraction of the first module that I activate. So I'm only activating nodes in the first module, and I'm measuring how far does the cascade spread. And that information is encoded in color, so the yellow means the entire system is active. Green means that only the entire first module is active, and blue means only a subset of the first module is active. Now, as you step to the right, what you're doing is increasing degree heterogeneity. So here I have Poisson degree distribution, and here I have a power law degree distribution with exponent -3. And then here I have uniform seeding versus maximum degree seeding. So if I don't bias my seeding according to degree, then the more heterogeneous networks are more difficult to get a global cascade on. But if I target the highest degree nodes, it becomes easier. And this is analytical and numerical. So I know there's a lot of information here. I just wanted to pack it out. Right. So this is perfectly reasonable. If your network is highly degree heterogeneous, you have more very high degree nodes. And so those are going to be correspondingly much more effective as seeds of a cascade. And this is perfectly analogous to some classic results about percolation, where your problem is not a cascade process, it is, does the network remain connected when you remove nodes? Okay, so any questions on this section? Yeah?
Does your analysis of the simplified model give you any insight to go back to your uncanny valley model and dig deeper?
That's a good question, and I haven't really thought about it. Well, I've thought about it a bit in that you can take that uncanny valley model and add in a bunch of assumptions about parameter values and derive a model of this form. You can say under lots and lots of assumptions, then a species will survive if and only if some fraction of its neighbors are still around. So you can, in a limited sense, map that onto this, but in my mind, that is more of just a qualitative, okay, this is not too far from where I wanted to start. Yeah.
Can I ask a maybe tougher question?
Yeah.
Related to your general theme?
Yeah.
So the uncanny valley models, I'm sure you say closer to the real world, right?
Yeah.
Which of these two models helps us understand the real world better?
That's a great question. Which of these two models helps us understand the real world better? Okay, which one of these sets of results helps us understand the real world better? This, I think, because, I mean, I could take more responsibility and say I just didn't follow through with that uncanny valley model, and there could have been some actual valuable, more detailed insight that I just didn't arrive at. But this, I think, so, yeah. It's a tough situation because in this model I've stripped away so many details that I can make sort of unambiguous statements about degree heterogeneity does this, targeting by degree does that, modularity does that. So those are nice, but they're sort of limited in how directly you can apply them to a real system, or a more realistic system, such as that other model I presented. I don't know if that answered any of what you were asking, but okay, thanks. Yeah.
Did you try removing stochasticity from the more complicated model? And what changed?
Yes, I did. I don't exactly recall, but yeah, I definitely did try that and tried like collapsing, like the alpha parameters were distributed from 0 to 0.5, and I just collapsed them to the same value, and that gave me a lot of symmetry. That was nice, but yeah, I mean that. If I was going to dig back into this, I think I might use that as one starting point. Okay. All right, so bring it all back home. Just a few sort of object level insights from these 3 chapters. From coupled entrainment, we learned that phase and frequency locking can be subtly interrelated. They're not identical, they're not completely at odds with each other. From coarse graining, we learned that synchronization can be viewed as a sort of dimension reduction, and that network and dynamical symmetries together can let you derive a low-dimensional model. And from this cascade study, we learned that network structure together with initial conditions determine the outcome of the cascade, which I think it's clear, and statistical regularity, meaning that nodes in the same module are interchangeable. It lets us write a low-dimensional model, so we can treat them as an ensemble of equivalent things and write a statistical law that governs them. And then some meta lessons. Toy models show cool behavior while being simple enough to understand intuitively. So I think toy models are a great sort of paradigm to work in to build something like understanding of general principles of collective behavior. And I'd like to think I learned a bit about what makes a good toy model and what makes a less good toy model. It should be simple enough to capture what you want, but no simpler. I think we've heard this many times from many places. And in particular, some like specific mathematical properties, symmetry, linearity, and low dimensionality are significant in making a model tractable. So that's it, and before I open it up to general questions, I just want to point out that this wouldn't have been possible without the concerted effort of many, many, many people over many years. First off, my family, my research group led by Raisa, the Santa Fe Institute Complex Systems Summer School that completely, I think, turned around my last year of grad school, and my collaborators at Los Alamos, Eric for getting me in the door, Anatoly for sort of working with me directly over 3 summers, and Andre for participating in the last sort of year and a half. So, thanks.
Do you have any questions for Jordan? Well, I guess I had one. Could you talk a little bit more about how you found the dynamical clustering?
Mm-hmm. Yeah.
Like, is that a unique method, or?
I believe it's unique. I don't have like a proof that it's unique. So what I did, like pragmatically, is just to take each oscillator, compute its phase, and then compute a long-run average frequency. So like how many cycles did it complete over 1,000 units of time, and then cluster according to that. So I said, like, I'd do an initial clustering according to that, say, group together ones with similar average frequency, and then look and see, are these actually phase locked? So did their phase differences ever exceed pi? I believe that that is a valid method and is not going to have any false positives or negatives. But yeah, it's fairly heuristic. Yeah. Okay.
Any other questions?
Then what does the structure and the dynamic partition mix? Mix the
Going back. This?
yes.
So, what's your question?
So how do you mix these two things?
So I'm taking, in the language of partitions, it's a meet, which is, I find the coarsest partition that refines both of the original ones. So the reason that this is not comparable is that this dynamical module extends over two structural modules. So I'm just giving it its own module. Yeah. So it's basically like pairwise intersections of partition elements. That's the way you can think of it.
Follow up on that
Yeah.
then, so in the most extreme, everyone would have their own module.
Right.
And
Right.
then
Right.
if it had your structural and dynamical met, we would have 3 modules, and they would correspond to that.
Well, if the dynamical partition was everyone in their own module, then the meet would be equal to the dynamical one.
Mhm.
So I would get 15 modules, right? Yeah, is that what you're saying? Okay, cool. Yeah, so that you could think of as a bug, but I kind of think of it as a feature, because what that's saying is, sorry, I can't aggregate variables. This is the most concise description I have of the system. Yeah. Yeah. Okay. Anything else?
Let's thank Jordan again.
Cool. Thank you.